So, we will start the afternoon session with Andreas Dilger for Lustre 2.16 and beyond. Your turn.
Andreas has been involved in the development of Lustre since its inception, from early prototype in 2000, before the founding of Cluster file system, so several companies over the past 20 years. Andreas has been one of the lead Lustre developers. In 2012, he took over the role of Lustre principal architect. Since 2018, he's Lustre CTO at Web Cloud DDN.
Thank you. Hello, everybody. I'm talking today about future development in Lustre. Peter has covered some of the, areas in Lustre 2.16, and so, unfortunately, we don't have a 2.16 out yet. So I'll be mostly trying to talk about some of the newer things that have been making its way into 2.16 while we're waiting for the IPv6 to finish, as well as lots of things that are ready, ready to go or underway for 2.17, and a little bit about features that are under discussion or early development for 2.18. As you can see, we have a slow but steady set of features coming in at each release, and I think that there's, while Lustre has already a lot of things, there's always new improvements and optimizations that we can add in. At the bottom level, LNet and networking is, IPv6 is a major part of what's coming in with the new release. And that's actually been a project that has been discussed, honestly, for over 10 years. I was looking back at the history of old presentations in the Lustre user group, and I think, 2011 or maybe even earlier than that, there was a presentation, with a title along the lines of, "We really need to get IPv6 going soon."
It was IPv6 is long overdue.
Okay, even better. Yes, that's what it was. And so it's really long overdue, but it's actually being developed now, and so that's a great thing. So that'll give us, as almost anybody's computer these days is actually, configured and using IPv6 at various times. It has been less of a problem for Lustre from the point of view that in many cases, the deployment of Lustre in data centers is often using a private network. And so, all of the compute nodes are not public facing, and they can be in a subnet that's isolated. And so the lack of IPv6 support is not in itself a hindrance in those kind of environments. In cloud deployments, which is becoming increasingly more popular, having IPv4 addresses for all of your nodes is potentially problematic. So having that support there is important. One of the good things is, being forward-thinking. In case IPv6 isn't large enough, there is support for larger address spaces. In case, we've been looking at various things instead of needing. So one of the configuration things we need for InfiniBand is all of the InfiniBand interfaces need to have IP addresses in order just to establish the initial connection and find the address of the node. We don't actually use IP for anything in that case, but we use IP over IB to address the nodes. And there's been discussion, with James a bit about, can we use direct IB GUIDs or some other type of name service to do direct IB address lookups without having to configure IP, which is sometimes an annoyance for large clusters. What else? the underlying, I don't think you're presenting, James, this week. No. So I'll cover this a little bit more. One of the good things is it's fairly well compatible with IPv4 in the sense of many of the data structures and the codes haven't had to be duplicated or replaced. We've done a lot of internal work. That's mostly we being James and Neil Brown and the other LNet developers. I'm not a network person myself. And so all the plumbing has been done. Some of it already went into the Lustre 2.15 release, but the last bits that are happening are really in the interface where compatibility matters in terms of configuration logs, the interface up to user space on how to set up IPv6. And that's really change logs have NIDs in them to identify which clients are doing operations and things like that. And so there's still some work in there, but I don't know the exact numbers, maybe James who knows, but I'm guessing there was probably 150 patches in IPv6 and we might be down to like 10 or 15 or something like that. So it's very close. And a lot of that, as part of that work, quite a bit of other infrastructure cleanup has gone through. I mean, Neil Brown is a seasoned kernel developer. He's one of the maintainers of NFS in the Linux kernel. And so he has a good eye for, what is good code and what is clean and things like that. So a lot of cruft as part of this project is sort of ancillary to IPv6. But there's been a lot of cleanup, and the code base is 20 years old. So what was modern in the Linux 2.2 kernel, whatever, when it was first implemented, has been replaced, and so that's quite good. Some other areas for LNet. Multi-rail, discovery and things like that have been improved. As a motivator also from having the IPv6, some work has been done to configure server nodes more transparently and avoiding hard coding of addresses. That work isn't quite complete yet, but some work has been done in that direction. On the client side, there's a continuing stream of improvements. I'm going to move this mouse pointer out of the way. The continuing stream of smaller improvements in terms of performance and ease of use. In 2.15, parallel directory renames. It's ironic, it's been around for 20 years. We've only had one lock for doing renames for the whole file system, and that was fine for HPC jobs. And then suddenly we got into a whole number of customers that are doing financial services, and I think they were used to using NFS where there's not atomic operations, and so they would implement atomic by doing a rename on every file after it's created. And you can believe that really hurt having one lock to do all of the renames, so we implemented parallel renames. That's only within a single directory. Right, so we can do directory renames within the same directory, and we can do file renames within the same directory. And that's it, solved, 95% of the problems there. And so that was a nice improvement. LFS migrate, lots of things on the user space in terms of usability. Migrate has a bandwidth limit because we sometimes want it faster, but in cloud environments, you also want it to go slower. So you can say, don't transfer data more than 20 megabytes a second, right? And a steady stream, I mean, there's one line here was code updates for newer kernels, but that's an ongoing task, and it's really been kept up to date quite a bit by Sean Tanchef at HPE. And another interesting one that's been around for a long time, and you wouldn't think that 8,000 Lustre devices is a limit for people. But what actually came about is systems, clients with mounting the same file system multiple times in containers and things like that. You have, a system with 40 MDTs and 150 or 200 OSTs, and then you mount it 20 times on a client. and suddenly you're running into your device limit, and so that's been fixed. Patrick will be talking about unaligned direct I/O. That's a big performance improvement. Also buffered I/O with direct I/O. Also Patrick. Client-side data compression. Artem will be talking about that, so I won't go into any details. Other, incremental improvements, erasure coding, is one line here, but that's something that was started a few years ago, but, the next thing that James said he's working on is the erasure coding at the Lustre level after IPv6. And so that will be, again, something that allows resilience, above and beyond what the hardware can supply, and I think it'll be a welcome addition. Client-side data compression, just a quick overview because Artem will be covering all of this. Essentially, it's splitting a file into chunks and compressing the individual chunks on the client. We have lots of CPU power on the clients, right? Hundreds of cores now per node, and in some regards, you'll get space reduction and potentially bandwidth improvements for free because often you're waiting on the constrained resource, which is, the network and the server bandwidth. And so I think there's a high potential for improvement here. I'm not going to cover all the details. I have a full deck of things because people look at these things afterwards, so I like to list all of the features. Other improvements on the server side is, really trying to take advantage of newer capabilities, particularly flash. I mean, Lustre does very well with MD, with hard drive based storage, sort of a dying breed in that respect. But even at lunch today, I was reminiscing about the days when there were disk based MDTs, and it seems crazy today that would be the case, but now we're getting into a single OST that's over a petabyte, right? There's requests from deployments 1.5 petabytes or more for one OST, just because of declustered RAID and having very large 20 terabyte plus drives and 40 or 80 of those into one declustered RAID group to get a better rebuild time. And so being able to handle that, one OST that's bigger than the whole file system used to be. And so there's different challenges there, and we're addressing quite a few of them. Having overstriped files that have 2,000 stripes in them, they have very large extended attributes, and journaling those consumes a lot of space. Billions of objects on one OST gets into some scaling issues, and we've addressed that. And it splits up, instead of, there's not a totally flat directory space for objects, but it was only a sort of one level directory tree, but even though there's not a scaling issue in that directory tree, you don't get very good locality anymore if you have each file create is being splattered across a huge number of blocks. So instead we're looking at aggregating temporally objects that are created at the same time, so you get like a few million objects in a directory tree. Then we move to a new directory tree that has, it's 30 million, 32 million is the limit, and so that aggregates them. So when you're creating, you're using the same blocks, and then typically you delete files in batches as well, and so it will read these blocks from disk, do heavy updates in those blocks, and then they can drop out of cache, versus having a huge directory. Even though our directory is scaled to hundreds of millions now, that was not very efficient. Nice feature, read-only mount of the underlying devices. So we actually you can mount a physically read-only OST, for recovery purposes, or if the hardware is failing and you don't want it to do any changes to the underlying storage. Peter mentioned LL job stat, and that was actually a relatively quick little tool that somebody wrote, but it's perfect for the, and we've used it a whole bunch of times since it's been written. Somebody's like, oh, our OST is slow, our MDT is slow. Who is doing that and why are they doing it? The information was always there. It's just not very easily accessible. And so we've also added some size histograms to the job stat, so you can get a little snapshot. Is this job doing 4K IO, 1 megabyte IO? It was in the BRW stats previously, but only aggregated for the whole server, and now you can split it out per job, which is nice. And coming in 2.17 is some work that's shown some actually really good promise. I don't have a graph, or it's just been submitted for a paper. But having a write-back cache for small IOs on the server can help performance for poorly formed IO sizes, right? We've always done large IOs directly to storage because it's more efficient than going through the page cache on the server. But for small IOs, it's worthwhile to pay that extra cost to add the data into the memory of cache of the server, so that you can aggregate that IO across multiple clients and across multiple write requests, and then submit it to the underlying storage in one shot, right? So there's a cutoff. It's kind of dynamic. 64K is going to be the default. I think not totally coincidentally that aligns with IOR hard write workload from the IO 500 benchmark, but it also, from our testing, that's a good cutoff size for if you have larger IOs, you're still better off just submitting them straight to storage. And by doing, and Patrick will talk about the direct writes, but by doing lockless writes from the clients, we also avoid lock ping-ponging. And so there's a whole number. I think we're seeing 5 times improvement for that, size of IO, which is pretty awesome. On the underlying storage side, LDiskOS is seeing quite a bit of improvements. The MBAlloc, that's the low-level block allocator. We've had to do some work, like I was saying, for the large OST sizes. At 1 petabyte, you have 8 million block groups to allocate from, and so selecting which one to allocate from is a bit of a chore. And so having it, we've added some improved, well, we didn't do it as upstream. Google and IBM did that, but we're backporting it into the production kernels we use. And so those ones have ordered lists. So if you're looking for a 1 megabyte or an 8 megabyte allocation, you can just do that in order one and find a group. And then you don't have to do any kind of searching, so it's very efficient. We did some improvements in MakeFS and using a newer feature in ext4 to aggregate the metadata. And that's helping avoid lots of seeks. Again, we were testing 1 petabyte OSTs, and it would take, up to 10 minutes to load all of the metadata once the file system is mounted. Hybrid storage devices is something we're just experimenting with, allowing you to have both flash and disk in the same logical device, and then ext4 or LDiskOS is smart enough to decide, should the metadata go there, should it go to disk devices, and I think that's going to be a big win for large hard drive based storage. Other things, E2FSCK improvements, these are just, incremental improvement as we're going through, understanding what the requirements are for such OSTs. Sebastian has talked about security, so I won't go into very much here. We did FSCrypt, that's all been released. Kerberos improvements is ready for 2.16, and some of it's already landed. Node map, lots of improvements in node map, so you can do all kinds of administrative controls for subdirectory mounts, because, you know, in the old days, Lustre, we tried to aggregate all of these resources to make, you know, the clients work, but now the clients are so huge, right? The DGX client, it has, you know, 4 sockets, 200 cores, you know, terabytes of RAM, and then people want to subdivide that to have multiple tenants running on one node, and so subdirectory mounts and node maps to restrict access and control access in slices of the file system. And so lots of work is being done in that area. Role-based access controls, so you can have root on a client, but it's not really root, it can't do everything, right? Various things like that. C groups, memory constraints to limit memory usage on the clients. On the metadata server side, there's, again, a number of different improvements. One I liked, even though it's 2.15, I like to re-emphasize this one because it was super important. The MDT space balancing, it's just been a godsend for, you know, anybody that's running a newer version of Lustre. You know, we still have customers running the pre-space balancing version of Lustre and its exascaler, and you know, it's just a maintenance administrative burden to manage that. What's that?
It's 212 based.
Yeah, and it's in 2.14 in 2.15, sorry, in the community tree, and so that's a big win. There's also other improvements, improving the inode migration, I mean, which is much less important to do now because the space balancing, you have systems now, 48 MDTs, I think, is the largest one we have now. And those are, you know, staying within a few % of each other with automatic space balancing, which is great. Better recovery. This is actually one of the projects that Peter was talking about in Hackathon, storing the job ID in a user xadder, user.job. And so that's actually giving you a little bit of provenance on which process or which MPI job was creating a file initially. And so that's actually quite nice to be able to debug, you know, who caused this file or what process created this file. Was it rsync? Was it, you know, even for users, because it's a user visible xadder, they can see, oh, I submitted that job and it was with these parameters, and this is why this data file is the way it is. So that's a pretty new one from the hackathon. More optimization in terms of locking and cleanups in the DNE code. And, you know, we're going to start working on improving some of the underlying infrastructure on MDTs to try and make them more robust in 2.17. And that's sort of the start of a multi-phase project. So one of the bigger features, one of the two, you know, key features in the 2.16 release is the batched cross-directory stat ahead. And so essentially we've had stat ahead as a feature in Lustre for a while, which is essentially, it's like read ahead, but for file attributes in a directory. And so if you're doing a read dir and then you stat every file in the directory, the MDS would detect this pattern and start sending out RPCs to the MDS to prefetch the inode attributes. And then in the next phase, it started prefetching the OST attributes. You would get the file layout back and then start fetching the OST attributes. So that would make your ls-l or whatever faster. And what's happened is we implemented some infrastructure. It's part of the project I'm going to talk on next. But we put in batched RPCs so that instead of sending, you know, thousands of individual requests to the servers, now we can send, you know, give me the attributes of the next 100 objects, right? But and starts here as get attrs, but it's going to be used later for batched updates as well for the metadata write-back cache, which I'll cover in a minute. And so we saw a fairly, you know, good, nearly double performance at a macro level benchmark both for individual directories and for a shared directory. So it can detect, it's optimization for regular workloads, but in some workloads where you're having multiple threads creating files with a regular pattern, right? Every MPI rank is writing out some checkpoint file, and they have a systematic file name. It can prefetch those file names by doing pattern detection on the names themselves, and so you can do prefetching of attributes, right? Like in the bottom case where it does strided detection read ahead. And so this was implemented as a way to start getting both, a useful performance improvement, but to start getting the infrastructure for the metadata write-back cache into the tree and to reduce the amount of outstanding code. So the write-back cache is, as it sounds, it's being able to do local modifications on a client without having to do a round trip to the metadata server on every file operation. And even though clients, today will do read caching of operations, any kind of update would previously need to talk to the MDS. And so the write-back cache is doing local operations. And the way it does that is it will get an exclusive lock on a directory, typically at make dear time, and then it has exclusive content control of everything inside the directory. And so it's sort of the Pandora's box, if you will, or maybe Schrodinger's cat is better, that the server doesn't know what's inside that directory until somebody, pokes into it. If another client tries to get into the directory, the client has to flush one level of cache down to the server, and then it will lock every other subdirectory. And then if the server is trying to poke down one path because another client is accessing it, it only has to flush out the parts of the cache that belong to the specific path name that's being accessed. And so it allows, totally, this is all cache coherent across the whole file system. But in many workloads where somebody's doing an untar or a make or whatever, and they have, a new directory tree in genomics and machine learning, quite often you'll untar a data set, operate on it, and then delete it. And so this is perfect for that kind of workload. And it's also, transparent to applications. They don't have to do anything to improve or change their behavior to get benefit from this. And so the code is in terms of development, it's quite, it's quite far in development. There is definitely going to be a lot of work to get it all landed in the 2.17 release, but it's waiting for 2.16 to go out the door. It's covered quite a lot of the infrastructure quotas and memory management and these various things. And we did see, in testing it, there was a whole presentation on this feature at, I think it was Supercomputing last year. And it was, very good performance speed up for certain workloads, 10 to 100 times is what I said here. And there's, I think it's very useful. I think that's my last slide. Questions?
Thank you, Andreas. If you have any question, quick questions, please.
It's not a question, but schedule slips left are so rare as to be unheard of, but Unaligned Direct I/O is in 2.16. It's merged now. So you have it for 2.17.
Unaligned Direct I/O is?
Yes.
Oh, I thought you were still working on it. Okay.
No.
Other questions?
Andreas, I think it is not mentioned in your slides. What about the CCI feature, client container image?
I didn't. I mean, I put in a new slide about ext4 and I took that one out. So nobody is really signed up to work on that yet. So it's a client container image. It's been in some of my other presentations. It's essentially using an ext4 file system instead of a tarball so that you don't have to untar your workload every time. You can just mount it and direct access. It's not on the roadmap. I would hope we can work on it, but it's not scheduled for any particular release yet.
Okay.
Thanks, Andreas.
Thank you.